of rational expressions. But talk about a few other things. These we haven't touched on how to integrate these two actual problems. We have a dx here. But there are some we have, and we are going to use various techniques on them, and a lot of it depends on the degrees of numerator and denominator. The degree of the top here is 1, the degree of the bottom here is 2, the degree here is 3, and we'll speak to more along that as we go. If we have, though, let's start off with, let's don't do those, maybe come back to ones like those. Let's start with 5x squared dx. And yeah, this is actually one we have spoken to before. If you're dividing, if your rational expression dividing by a monomial on the bottom, then the idea would be split it up, divide it up. In other words, divide each separately by x squared. X squared divided by x squared, 7x divided by x squared minus 9 divided by x squared. Do them all separately, and usually it all washes out here. All right. Of course, the x squared is canceled there, so you just have 5. Here the x goes into the x squared, so we just have an x on the bottom, 7x, 7 over x. And then here, 9 over x squared, well, nothing really there to do. And yeah, this helps us out because each one of these separately can be done, right? The integral of 5 dx, the integral of 7 over x dx, and minus the integral of 9 over x squared dx. I don't know if you necessarily have to write it all out, but that's what we're doing, right? We can do those in separately. Here the integral is just 5x. What about the second one? Yeah, that's our ln, isn't it? If it's 7 over x or 7x to the minus 1, however you want to think about it, that's ln of x, isn't it? 7 ln of absolute value of x. And then this one, what about that one? Well, that was just power rule, isn't it? 9x to the minus 2 is what that is? Yeah, so that's just power rule. Add 1, so we have 9 divided by negative 1, x to the minus 1. Yeah, plus 6. So those are relatively easy. We'd wind up with 5x, 7 ln of absolute value of x, plus 9 over x, or x to the minus 1, however you want to write that. But okay? So that one we've hit upon before, but I don't think it hurts to do it again. Okay, well, this one, next one, actually similar. We'll do it, we'll do this one in a similar fashion. Let's take a look at this one. This one's going to be the integral x squared plus 2x plus 3 divided by x minus 2 dx. And the point on this one, of course, it's not a monomial anymore, so it's a little bit different division, but we do have the degree of the top bigger than the degree of the bottom. And anytime you have that, go ahead and start off by dividing. When the degree of the top greater than the degree of the bottom, yeah, if your degree of the numerator exceeds the degree of the denominator, then divide it out. However you want to, synthetic, in this case we could, but long division, sometimes you have to break out the old long division, so it'll always work. Yeah, divide it out. Here's what we get. X divided by x squared divided by x is x. X times minus 2 is x minus 2. X squared minus 2x. Change the sign, so it's 4x. Bring down the next, plus 3. 4x divided by x is 4. 4 times x minus 2 is 4x minus 8. Change the signs. I get 11 remainder. And so I can rewrite this then. Here's what I'm going to do. Using the result of my division there, couldn't I rewrite this division as x plus 4 plus 11 over x minus 2? Couldn't I do that? So I'll rewrite this by the result of my division this way. With me? Well, why would I do that? Well, again, that sets up 3 terms, all integrate all those 3 terms separately. X dx plus the integral of 4dx. Don't necessarily have to write this, but that's what we're doing. Okay? That was just 1/2 x squared. That's 4x. Now this one, what about the last one? It is technically u substitution, but when you do the u substitution, the du is equal to dx. You see what I'm saying? This that's going to be u, and so I'm going to have 11 over u, so I'm going to have another natural log. But since again du equals just dx, it's really just you see it's going to be 11 natural log of x minus 2 absolute value. Let's see. Is that okay? I need to do. It's just once you do the u substitution, you have the integral of 11 over u, which that's 11 times the natural log of u, which u is x minus 2. So, all right. So there's that. Sometimes you just divide. But of course, much more can happen. Well, let's talk about this one. I guess another dividing one. Can we divide on this one? 3x squared divided by x squared plus 1. 3x squared over x squared plus 1. Would it help, you think, to divide there? Yeah. If the degrees equal, degree equals also divide. Now, 3x squared, divide that by x squared plus 1. What you got? Well, 3x squared divided by x squared is 3. 3 times x squared, 3x squared plus 3. Change the signs there, so I have a minus 3. So this one becomes 3 minus 3 minus 3 over x squared plus 1. That's the integral now. And in this case, it helps me because what about this integral? Well, that's just 3x. What about that integral? What about the second integral? What's the integral of that? Inverse tangent. Yes, that's 3 times inverse tangent. Okay, so sometimes that can happen. So if you're dividing by a monomial, if the degrees equal, if the degrees of the top is more than the bottom, you divide. So all those cases. So what we want to look at mainly here today then is when that's not true, any of that's true. What we're going to look at now is when, maybe we'll sneak one of these in, but ultimately it'll work back to the degree of the top is less than the degree of the bottom. That's what we're going to talk about mainly the rest of the time here. And a new thing. We haven't seen this probably before. Okay? All right. It's called partial fraction decomposition. Like I say, we're going to use this when the degree of the top is less than the bottom, and there's not, the usual suspects, and there's no U substitution. We're always going to try U substitution. If it works, we don't have to go into all this, or the trig, inverse trig functions, or the trig substitution. That gets into something else. That's square roots of stuff. So, but yeah, if the U substitution doesn't work, or there's not a nice trig, inverse trig function like we saw in the previous one, we are going to try this partial fraction PFD. Look at this. 5x minus 3 over x squared minus. I'm just going to go through a partial fraction decomposition, and then we'll do one in the context of an integral. Here's what that means. What that means is, well, if you notice here, 5x minus 3 over x squared minus 2x minus 3 is also could be written x plus 1, x minus 2 on the bottom, factor it out. What we're going to do is this, basically this. We usually go the other way, where we combine two fractions into one. This is going to reverse that. I'm going to take this one fraction and make it into two fractions, because I have basically two denominators. Okay? That's the idea. So I'm going to split this one fraction, started with this, but back to that, into two fractions, which one of the fractions is going to have x plus 1, and then the other one's going to have x minus 3. So you see what I'm saying? It's reversing what we normally do. Yeah, and it's, adding. It may turn out to be subtraction, but it'll all work out. Now, the thing is, we need to figure out what the tops are. And the way we usually start is just calling it A and B, if we've got two. C, the third one, and there's some other wrinkles, twists, turns as we go along. So I need to figure out what the fractions are, and it basically amounts to, well, what number do I need to put on top of the x plus 1, and what do I need? Okay? So that's called decomposition, fraction decomposition, because I'm decomposing it from 1 into 2, whereas usually I go the reverse. Okay? So how do I do this? Well, the way I do it, let me rewrite to it. The easiest way to think of it is, our least common denominator would be what? This denominator. Is just multiply both sides by that, or multiply each thing by that. So I'm going to multiply the x plus 1, x minus 3 times this. Of course, that's all going to cancel out. Then I'm going to multiply it by this. And then I'm going to multiply by that, the b. And you won't necessarily have to write all this down, because you can see what's going to happen. Of course, those cancel, so I just have 5x minus 3 here. The x plus 1's cancel here, so I have a times x minus 3 for that second part. And then the x minus 3's cancel here, so I have b times x plus 1. Okay? Keep this side same, but here, what have we got? Ax minus 3a, and then bx plus b. Okay? With me there so far? Well, the way you go from here is notice on the left side I've got 5x, and then on the right side don't I have 2x terms? I've got ax and I've got plus bx. Well, essentially what we're doing, I won't necessarily write this every time, but regrouping here, couldn't I say this, putting these together, basically I've got this, I've got a plus b, that's what's times x over here, right? And then the other, the minus 3a plus b, well, it's not times x, so wouldn't it have to match up? So wouldn't these things right here, the coefficient of this x would have to match the coefficient of this x. That's how this is going to have to work. So, yeah, a plus b is going to have to equal 5. Well, what that also sets up then, what about these? What about the minus 3a plus b? Wouldn't they have to equal up to the constant? Because that's what these are going to have to be. So the minus 3a plus b must equal negative 3. See that? Well, what about that? I need to figure out what A is and B are. What basically do I have here? I just have a system of equations. I just have a system of equations. So I just need to solve my little system of equations. However float your boat there. Looks like to me, change signs of one of them. Make the top or the bottom positive 3a minus b. Leave the top a plus b equals 5. Make the bottom 3a minus b equals positive 3. Just changing, basically multiplying everything by negative 1. And that's 4a equals 8, because the b's cancel. Move it up over here. So 3a plus a is 4a. 5 plus 3 is 8. So doesn't a have to be 2? Well, if a is 2, a plus b equals 5. So 2 plus b equals 5. Doesn't b have to be 3? There you go. A is 2, b is 3. So our decomposition is this. (5x) over this x squared minus 2x minus 3 equals 2 over x minus 1 plus 3 over x plus 3. Huh? Plus 1 minus 3. Yeah, that's what I meant. Okay. Yeah, there it was. 3 over x plus 2 over x plus 1. Okay? So that one fraction is those two fractions added together. And you can check if you want. Go back the other way, but it does work out. Okay. So, where does this apply? This applies because, let's say we had this integral. Is that okay? Any problems there to do? I think I got it all right. That's what I had anyway previously. So, okay. So if I have, let's say I throw an integral there, 5x minus 3 over x squared minus 2x minus 3. Yeah. Well, dividing is not going to help me there. The bottom is not an inverse trig at all. Use substitution. I don't think so. Well, let's rewrite this using this decomposition and see what we think there. So since this is equal to that, can I rewrite that as 2 over x plus 1 integral plus 3 over x minus 3? Those two are the same, so I can do that. Now, aren't these nice integrals? The integral of 2 over x plus 1, I can do that. 3 over x minus 3, I can do that. And again, just to let you in on a little secret here, if the top is just a number and the bottom is just x, not 3x or 4x or something like that, that's just natural log. Right? Because the u substitution, you're not going to get any different factor, like a 1/3 or a 1/2 or anything. This is just natural log. And it'd be 2 times the natural log of the x plus 1. And then this will be 3 times the natural log of x minus 3. Like I said, you can do that. If that was a 2x, then you'd have to do a little u substitution there. But that's technically what we're doing, but it doesn't affect it anyway. Okay? All right, so that's one application. Shall we try another? Let's try the integral of 8 over t squared minus 4t. T. Sure, you can. Go ahead and break it down. It does factor. Now, if that had been, well, on the bottom, t squared plus 4, then I could think about maybe an inverse trig function. But t squared minus 4t, there are things, but yeah, this is going to work nicely with this fraction decomposition. Okay, so what do? I take the 8t, t minus 4, and I split it into 2. I've got a over t, and then b over t minus 4, or vice versa. And so then I multiply everything by t minus 4. How much do I need to write that down? What's going to happen? If I multiply then everything by t minus 4. Well, that's just going to be 8. What's that going to be? A times t minus 4. And that's going to be bt. Or, in other words, 8 equals at minus 4a plus bt. So far, so good. Well, this one's a little bit different because, notice over here I just have an 8. I still, though, do have t terms over here. And so let me regroup here. The t terms will be a plus b times t minus 4a. So what do you see the system here as? What does the a plus b have to equal? Well, there's not a t term over here, so it'll be 0, yeah. If there's no t term, the t term is 0t. So this is 0t. So 0, the a plus b equals 0, doesn't it? The minus 4a, this is good because this is really easy. What does minus 4a equal? Minus 4a equals the 8. Yeah, and sometimes you run into that. Sometimes you just get a number right out of it because what about a? A has to be negative 2, doesn't it? Well, if a is negative 2, then negative 2 plus b has to be equal to 0. Add 2, you got b is 2. So we got a is negative 2, the b is positive 2 for my decomposition. So this becomes the integral. I'm going to decompose it then. It's going to be a over negative 2 over t plus positive 2 over t minus 4. And I'm in good shape because those are just both natural logs, aren't they? This one's going to be minus 2, the natural log of absolute value of t. And this will be positive 2, times the natural log of t minus 4. Let's see. Question? What's that? Oh, no, that's what I'm saying. This one did wind up being a minus.